Now, as engineers, I like to say that one of the first things that we do is we carefully review the scope and the specifications for the projects that we're working on. That way, we have a complete clear understanding of what is required from us to deliver to our different clients. So we should treat the NCS B exam the same way. We need to carefully review the specifications and the scopes given in the NCS B exam. So here on this slide, we see the specifications for the geometrics-based breadth topic. Now, you'll be tested on 3 problems in the P exam for geometrics, which is about 7.5% of the overall grade of the breadth portion of the exam. Now, on geometrics, you have 3 overall sub-concepts that are mentioned in the exam. The first one is basic circular curve elements, which are your horizontal curves. And this is covered in CERN chapter 79. The next concept is basic vertical curve elements. So those are your vertical curves. Those are covered in CERN chapter 79. And the last portion is traffic volume, which includes vehicle mix, flow, and speed. And that's covered in CERN chapter 73. Now, these geometric type of concepts are more inclined into the transportation area. So you've been working in transportation, knowing horizontal curves, designing vertical curves, and evaluating traffic volume. These concepts should come as second hand to you. Another key thing that I want to point out is that you'll be tested 3 problems on geometrics. So more than likely, you'll have 1 problem on horizontal curves, 1 problem on vertical curves, and then 1 problem on traffic volume. Now for the lesson, we're going to review these 3 overall concepts. First, we're going to start with traffic volume. Then we're going to go into basic circular curve elements. And then our last concept is going to be the geometric design of vertical curves. As you can see, all 3 topics and concepts listed by NCS are going to be covered directly through this lesson. Now, we have seen in other lessons that some topics are not covered because they're better suited to be covered in different lessons. Like when we were reviewing materials, there were topics on concrete and steel material properties that were not covered in the materials lesson because they follow better with the flow under the structural lesson. But for this case on geometrics, we're going to cover all the concepts on the NCS specs right through in this lesson. Now, note that this course is a preparation course. It's not a refresher course. It's not intended to teach you 100% new ideas or concepts that you have not seen before. It's not intended to replace 4 years of college coursework and 4 years of professional experience. So the intent of the course is to prepare you for the P exam. So you will get mainly 2 things out of this course. One is you will identify the areas that you're strong on, and 2, you'll identify the areas that you're weak on, where you need to cover additional material to further refresh your knowledge. And that can be seen as perhaps if you work in one part of the civil engineering industry that only deals with geotechnical engineering, you may be strong in geotechnical engineering, but you may require additional review of perhaps transportation topics, perhaps structural topics, and so forth. Now, having said that, there's some core prerequisite knowledge that you should have before we get into this full geometrics lesson. You should be already familiar with basic calculus principles and basic mechanics principles. Now, here are some reference codes and standards that we'll use to cover some of the topics mentioned in this lesson. We have the AASHTO Green Book, which is the policy of geometric design of highways and streets, which will provide you information on horizontal and vertical curves. And then we have the Highway Capacity Manual, which provides information for traffic engineers on how to design our highways and roads to meet capacity. Now, we're going to reference these codes and standards to review some of the theory and concepts that you need to know for the breadth portion of the exam. However, and let me highlight this, however, you do not need to look up values in either the AASHTO Green Book or the Highway Capacity Manual for the breadth portion of the exam. You do not need to look up values in the Green Book or the HCM for the breadth portion of the exam. However, if you are taking the breadth portion of the exam on the transportation subdiscipline, you will need to look up values in the Green Book and you will need to look up values in the HCM. So please understand that key distinction. The breadth portion of the exam is the general part of the exam, and you're not required to look at values in either codes or standards to solve problems for the breadth portion of the exam. So, having said that, that is why the CERM, the CERM, the Civil Engineering Reference Manual, is your best resource for the breadth portion of the exam, because the CERM provides a compendium of all the different formulas, theories, and concepts that you can refer back to when trying to solve a problem from the breadth portion of the exam. However, for the depth portion of the exam, if you're taking an exam, let's say in transportation, you will need to supplement CERM with the Green Book and the Highway Capacity Manual, and some additional manuals that are listed on the NCS specifications of reference codes and standards for the depth portion of the exam. Please realize that CERM does not have under specifications codes or standards for the breadth portion of the exam. So there's a clear distinction between breadth and depth. So let's start with our first concept of traffic volume. Now here's some key abbreviations when we're dealing with traffic volume. We have lane, kilometers per hour, miles per hour, P, which will represent a people, a person, or a pedestrian, a PC, which is a passenger car. And let me highlight because this is when it starts getting fun. And these abbreviations come straightly from the Highway Capacity Manual. And because they come from the Highway Capacity Manual, they just carry through because that's the main guide for traffic flow design. So that carries through for all the traffic design concepts that you will encounter. So starting with PC, that's our passenger car. And then we add a per hour component. So we have passenger cars per hour. So that's, you see, it's already starting to represent a flow of traffic. And then you have PCPHG, which is passenger cars per hour of green signal. So that's stating the volume of cars that can pass through a green signal. Then you have passenger cars per hour per lane. So that is giving you the flow of traffic through a specific lane or per lane on a different highway. So you have a multi-lane highway, you can be provided with passenger cars per hour per lane. Then you have the PCPHGPL, passenger cars per hour of green signal per lane. So that is the amount of flow of passenger cars that's going through a green signal divided by the number of lanes on a specific roadway. And then you have your PCLN or your passenger cars per lane, or you have your passenger cars per kilometer per lane, which is just almost like dividing your flow in a unit version and then dividing that per lane. Similarly, you have your PCPMPL, which is your passenger cars per mile per lane. Pedestrians can always be called ped, persons can always be called person, vehicle can also be called BEH. Now, another key one is the BPH, your vehicles per hour. Note this is different of passenger cars per hour. Vehicles per hour mean all your vehicles, trucks, buses, emergency vehicles, I said trucks twice, and passenger cars. So there are conversion factors to get vehicles per hour based on the percentage of trucks, the percentage of recreational vehicles to their passenger car equivalent. Then you also have vehicles per kilometer, vehicles per hour per lane, vehicles per kilometer, which is shown as VPK or VH over kilometer, and then vehicles per mile. So you will see that you may be asked to do some kind of conversion of traffic flow to get vehicles per hour to, let's say, passenger cars per hour per lane, or vehicles per mile to passenger cars per mile per lane. So you may be required to do some kind of conversion like that in a traffic flow type of problem. So it's important to know what this definition stands for, what this nomenclature stands for. Now the abbreviations in this table are also going to be used throughout the lesson and may be used in the exam. You may want to tap this table for this specific reason because you may be asked to find one over the other. And to be frank, even folks that use these values on a day-to-day when analyzing traffic flow, it is a little bit tough to sometimes keep tabs of the different abbreviations. So it's good to have them, to have this table tab as a resource that you can use during the P exam. Now let's go to traffic flow rate. One of the key concepts within traffic flow rate is that of design vehicles. Now, which are basically the representations of a variety of common vehicles, which is applicable to highway and road design. And you also design for a standard vehicle. And for standardized design vehicles, you need to ensure that the geometry features accommodate all commonly sized vehicles in that category. And this is given by specific designations in the AASHTO Green Book. Now, the AASHTO Green Book also contains information on wheelbase and turning radius. For the breadth portion of the exam, design vehicle information will be provided. If it is not provided, then the design vehicle can be assumed to be synonymous with any kind of vehicle. Now, design vehicle information gives you, for example, the bumper-to-bumper distance of a standard passenger car, or the bumper-to-bumper distance for a specific type of truck, such as WB50 and so forth. Now, all these design vehicles and their dimensions are referenced in the AASHTO Green Book. For the breadth portion of the exam, because you will not be required to look up values, tables, charts in AASHTO's Green Book, you will be given information on a design vehicle. So here's some information for traffic flow rates for standard design vehicles. Now, we also have two key things that are working out on this table. Before we get into the dimensions of the standard design vehicles, let me get to their symbol designations. So passenger car has a symbol of P. A single unit truck is called SU, and it can be a single unit 30 or a single unit 9. You have a single unit bus that can be bus 40. An articulated bus is an A bus. Combination trucks have a WB40, a WB50, a WB67, and many other type of designations. Now, recreational vehicles, which are also known as RV. So let me supplement this chart really quick. Now, recreational vehicles, which are also known with the symbol RV, represent a motorhome can be called an MH, a car and camper trailer is a P over T, a car and boat trailer is a P over B, and a motorhome and a boat trailer is MH over B. Now let's go through the different dimensions. So let me perhaps zoom out a little bit. So the dimensions are given in feet, and the parenthesis dimension is its conversion to meters. So a passenger car has a height of about 4.3 feet, a width of 7 feet, and a length of about 19 feet. A single unit truck has a height of 11 feet, 11 to 13.5 feet, a width of 8 feet, and a length of about 30 feet. And so forth for all the other type of vehicles. Now, know what this is doing. This is standard dimensions. What they are doing is they're providing you with a cube that represents that specific car. Right? They're giving you a cube dimension that represents that specific vehicle. I'm not the best at drawing. Let me try to get this graphic done almost right. I should have started with my planes. I should have just gone with my lines from the beginning. So what these dimensions are giving you are a height, a width, and a length. And a length of the vehicle. Now, why is this important? Think of horizontal curve design if you're designing a vehicle. Or perhaps think of vertical curve design if you're trying to design a curve to have clearance under a bridge. So you may be provided with information of a vertical curve, and then you need to find the clearance above, let's say a WB40 truck. You will then use its height dimension. Or perhaps you're being asked to calculate on a left turn lane that is, let's say, 100 feet long, how many passenger cars can be fitted in that left turn lane if you need to consider that they're going to have a space of 5 feet between them. So you will use the length dimension to determine that number. So many other ways that NCS can test you on the concept of having a standardized design vehicle represented by simply a cube or a prism. I shouldn't say a cube, it's a prism, a rectangular prism. Now there are also vehicular equivalents, which will give you the standard unit of measure for vehicular flow. And that unit will be the passenger car, which is the majority of highway traffic. So What I'm trying to say is, in addition to having standard vehicles for the dimensions of a specific design vehicle where you design for the geometry, when it comes to traffic flow, you don't really consider too much the geometry. Instead, you convert everything to an equivalent vehicle. So you can compare, let's say, intersections, apple to apple, or through segments, apples to apples. So we convert all the flow rate, which will be a mix of our recreational vehicles, trucks, and passenger cars, into a single standard unit of measure. We convert all of that into passenger cars. Now, this equivalency of vehicles are calculated using factors obtained for the highway capacity manual. And the vehicle equivalents are influenced by many factors such as the speed, the size, and the density. Now, converting everything to a passenger car equivalent is from information that comes from the highway capacity manual. On the previous slide, having standard design vehicles, that is more into the geometry. So this comes from the AASHTO Green Book. The AASHTO Green Book focuses on geometry. The highway capacity manual focuses on traffic. Two clear definitions, two clear distinctions that you need to be aware of for the breadth portion of the exam. So here comes the passenger car equivalents for general freeway segments. Now this will vary based on the type of segment. So a freeway segment is just like an interstate highway. And you can say how the passenger car equivalents may differ for perhaps a local road or a residential road. So let's go into these equivalency factors. So trucks and buses on a level highway will be about 1.5 passenger cars. Trucks and buses on a mountainous highway, a highway that has steep grades, will be about 4.5 passenger cars. And this is represented by your equivalent truck factor. Now, your equivalent recreational vehicles factor, which are your recreational vehicles, your motor homes with its different trailers, represent about 1.2 passenger cars on a level terrain for a highway, for a freeway segment, and then about 4 passenger cars for a mountainous segment. See how this comes from the highway capacity manual, from the HCM. So this is a conversion to get everything into passenger car equivalents. This is a very, very cute mistake. Even though we care about passengers, this is not a passenger care equivalent. It's a passenger car equivalent. What a cute mistake. Now, trucks, buses, and recreational vehicles will take up more space on a roadway than passenger cars will, and they tend to travel slower in upgrades. So they will degrade the quality of travel more than the same number of cars would. So in other words, the factor will always be greater than 1. In the same subject, smaller vehicles, such as motorcycles, can be used and having a factor less than 1. So the idea here under this passenger car equivalent is that trucks and buses occupy more space in a highway, more physical space, even if they were going at the same flow rate, at the same speed than regular cars. So that's what you can see in level terrain. It's almost like they're just simplifying they're going at the same flow and rate as cars, but they just have a bigger area. So they occupy, let's say trucks, 50% more space, and RVs, 20% more space. Now, when we have grades, our trucks, buses, and RVs are not going to be able to accelerate and move fast enough as a passenger car. Therefore, they will have this traffic shadow in them. So that traffic shadow takes up more space in the highway. So that's why when you have steeper grades, trucks and buses, will be about 2.5, and RBs will be about twice as much as a passenger car. And this shadow gets elongated the steeper the grade. That's why we have mountainous grades. RBs, trucks, and buses will take even more space than passenger cars. Trucks will take about 4.5 times passenger cars, and RBs about 4 times that of passenger cars. And here comes a key measurement on our traffic capacity, which is the level of service, which is the quality of service on a specific facility or through a specific facility that is experienced by the user of that facility. Now, level of service are graded such as you would grade elementary school paper. They're graded from A through F. And of course, A means, that's an A plus student. That's when you have unimpeded flow. That's if you're riding on an interstate highway, like at, let's say, Sunday at 7 in the morning, when there's absolutely no traffic. Or they're graded as F when you have gridlock, such as, let's say, you're stuck in downtown traffic right when everybody's leaving work to go home. So like around 5 or 5:30 p.m. when you're basically bumper to bumper traffic, or the traffic that you will experience at the end of, let's say, a big football game. Now, the examples for level of service are evaluated for highway segments, which are through segments, for intersections, which of course are intersections or crossing segments, are nodes in our transportation network, or crosswalks, which are where pedestrians walk or cross the street. Now, while it may be desirable to always get an A plus, to get a level of service A, it is unrealistic to get that in urban areas. It is only possible to get a level of service A when the volume of traffic is small. So because of the density of our urban areas, it is not possible to get high levels of service. So you will see traffic engineers being more than content with getting a traffic of level C or even a traffic of level F at an urban area. Now, the benefits of designing for a level of service A will also may not justify the cost of construction, because you evaluate your level of service at your worst times of your facility, at your peak hours. That's when you evaluate your levels of service. So imagine trying to design a freeway for a level of service A at a peak design time. Let's say when you have everybody coming out of the stadium after a Super Bowl match, right? It just will be just crazy expensive. We'll need to have 20 lanes in each direction to achieve a level of service A on the highway. Now, level of service is a function of vehicle speed and flow rate on the roadway. The relationship between the flow rate and the speed is also known as the vehicular density. The vehicular density is calculated by dividing the flow rate, which is in vehicles per hour per lane, by the speed, which is in miles per hour, and the result is in units of vehicles per mile per lane. Once the vehicular density has been calculated, the level of service can be found using values provided by the highway capacity manual. These values differ depending on the types of facilities being designed. Now, level of E is the maximum acceptable flow rate. This is when our facility is at capacity, when it's flowing at capacity. Now, level of F means it's highly impeded. It's a packed condition. And the evaluation of level of service will focus on the peak flow, on the peak 15 minutes of flow. So think of designing this huge facility, if you want to get level of service A, that will only have a level of service A for its peak 15 minutes. So because of this idea, this is why traffic engineers will be more than content to get a traffic of level F on a facility, because that traffic level F only occurs at the peak 15 minutes of each day. The remainder of the time, the facility may be functioning as a level of service B or even a level of service A. So this is the reasoning why it is deemed acceptable to have facilities at what will you consider a failing grade. Now, because traffic conditions vary greatly, this is why we design for a 15-minute peak. Now, the peak is obtained from the hourly peak traffic observed in the field. Now, if you see folks at an intersection or a freeway segment, sitting on lawn chairs with clickers, what they're doing is they're counting cars. They're conducting a traffic study. Or perhaps you don't see that so often so more because we're using mechanized units. So if you're driving through a driveway and you suddenly hear two thumps, thump thump, and you notice that you just passed what seems to be like a little hose in the middle of the street or a pair of two hoses in the middle of the street, those are activating traffic counts. Every time the tires pass through those pair of hoses, they will they activate like a pneumatic switch that counts that your car passing through it. And why do you have two hoses? It's in order to determine if you are a truck, if you are a passenger car, or if you are an RV. So next time you're riding on a road, on a boulevard, and you hear that thump thump, and you look at your rearview mirror and you notice you just passed over a black hose, please note that your car has been counted. Now, for roadways that have a lower level of service, it typically indicates that the roadway is functioning at a packed condition and can be interpreted that the roadway is less safe. Now, the notion that the roadway is less safe when you have a lower level of service is all related to density. There are more cars on the highway. And because there are more cars on the highway, first of all, they're all driving a little bit slower, right? But because there are more cars on the highway, statistically, there's a higher probability of having an accident or of having a crash, right? So that's why the more and more cars you have on the highway, the less safe the highway is, because statistically, there's just a higher probability of it being a crash. Now, this is what our primary measures of level of service are, and this is given in table 73.4 of CERN. So for a type of facility that is a freeway or a highway, it's based on the density of the cars, and this is measured in passenger cars per mile per lane. Passenger cars per mile per lane. For a basic freeway segment, for where you have weaving areas or ramp junctions, or for multi-lane highways. Now, the level of service for two-lane rural highways is based on a different type of parameter. It's based on the speed, or how fast can you travel on that two-lane rural highway, or the percent time that you spend following somebody on that two-lane rural highway, because sometimes you can't pass that person because it's prohibited on this two-lane rural highway. So the level of service will be based on the speed or the time you spend following another car. Now, for signalized intersections, it will be based on the average control delay, how much time you are stopped at that intersection on average. And that's typically measured as seconds per vehicle. So of all the cars that get stopped at this red light throughout the day, what is the average control delay? How much time is the average time a car has spent on that red light? And that is measured in seconds per vehicle. For unsignalized intersections, and unsignalized intersections are those that simply do not have a traffic signal, that do not have a red light. So the average control delay is also used for the level of service, and is also measured in seconds per vehicle. For urban streets, will be your average travel speed. How fast can you move on that urban highway? Now for mass transit, you have various uh, level of service parameters as persons per seat, vehicles per hour, people per hour, persons per seat, and so forth. Now for pedestrians is the space per the pedestrian or the delay the pedestrian experience at that specific facility, whether that be a sidewalk or a crosswalk. And for bicycles, is also based on the event or the delay and is measured as seconds per vehicle, and the vehicle being a bicycle. Note this is a compilation from all the different level of service definitions shown in the highway capacity manual. As you can see here, table 73.4, what it clearly highlights is that levels of service have different measures based on the facility under consideration. So please note that this is another key distinction and concept that you need to understand for the breadth portion of the exam, because you may be tested on a theoretical question. Now, you're not going to be required to look up a level of service at a table in the highway capacity manual, but you may be asked something about some factors on how you determine the level of service for a freeway versus how you determine the level of service for a signalized intersection. And note that this table will be your guide to solve that kind of theoretical type of problem or small little mathematical practical problem. So I will encourage you to go ahead and tap this table so you can have it for quick reference in the P exam. Now the next part on when we deal with traffic volume is the rate of flow. And this is equivalently the hourly rate at which vehicles pass a given point. And is measured designed for a given time interval and is typically used for 15 minutes. Now when it comes to the design capacity, this is the maximum volume of traffic that the roadway can handle. And this is based on the level of service. And it's kind of given by the volume to capacity ratio, which is equation 73.3 of CERN. Now, the subscript I in equation 73.3 represents the level of service. So you can have your volume to capacity ratio for a level of service A, B, C, D, E, F. The ideal capacity for freeways is considered to be 2,400 passenger cars per hour per lane. 2,400 passenger cars per hour per lane. That is the ideal capacity for a freeway. A volume capacity ratio of 1 indicates that the facility is at capacity. A volume capacity ratio of 1 indicates that the facility is at capacity. Another key foundational core concept when it comes to traffic flow design. We also have traffic volume parameters. Note that volumes may be considered for both directions and we combine the volumes, or for all lanes on one direction, or for an individual lane. So you may be asked a problem in the P exam where you may have a little bit of a quick check done by NCS to see if you're paying attention. So they may say they want you to calculate something for both directions of traffic, or for all lanes in one direction, or for one lane in the problem prompt. One key way to do this is to say that traffic on a road has a 40-60 split. That means 40% goes in one direction, 60% goes in the other direction. So they may give you a total amount of traffic on that roadway, both directions of traffic, and you're being asked to find what is the peak hour equivalent for the direction of traffic that takes the most cars. Given that the peak hour factor is 3 or something like that, and they give you that it is a 40-60 split. So they will be testing you on this concept of that volumes can be considered either for both directions, all lanes, or an individual lane. And here's where we start getting into the average daily traffic, which is known as ADT. not to be confused with the security company, and the average annual daily traffic, which is AADT, which the average annual daily traffic and the average daily traffic may be either one or two-way directional traffic. And I like to pick a little bit to my traffic engineer colleagues because I think, in my perspective, traffic engineering is one of the parts of the civil engineering profession that has the most acronyms. So that's why I like to pick on them a little bit. ADT and AADT can be a little bit confusing because the units are the same. Note that the ADT, the average daily traffic, is calculated by dividing a given traffic count by the time over which the traffic count took place. So for example, 10,000 cars over 10 days means an average daily traffic of 1,000 cars per day. The average annual daily traffic is the total number of cars that travel a road in a given year divided by the number of days in the year. So they kind of seem to represent the same, but they are used differently in solving traffic volume type of problems. And that takes us to the design hour volume. The design hour volume is the 30th highest hourly volume expected in the design year. So what we do is we design facilities and we evaluate them for the design year, and that design year may be in the future because we want to design the facility to operate up to 20 years from today. So design year may be 20 years in the future. The design hour volume, it is not an average and it's not a maximum. And the design hourly volume is two-way volume unless we're being said otherwise. And that takes us to the K factor. The K factor is simply a ratio of the design hourly volume to the average annual daily traffic. Note how the K factor, you need to use the average annual daily traffic because the design hourly volume is also being seen in a perspective of a year. Is the 30th highest hourly volume expected in the design year. So they both have this point of view for a whole year. So for the Howey capacity manual, default values are 0.09 and 0.10. So your design hourly volume is going to be a tenth of your average annual daily traffic. Now, the design hourly volume is also nicknamed by traffic engineers as the 30th hour volume. The K factor is the ratio of peak hour traffic to the average annual daily traffic. The design hourly volume is what traffic engineers, use to design the roadway. The K factor can be used to estimate what the design hourly volume is based on the average annual daily traffic. The Howey Capacity Manual recommends typical values based on the area on which the roadway is located, such as urban will be different than rural values. It is usually best to measure the K factor directly from traffic observations. Nothing beats having a direct study of the actual facility you're going to design or improve. That is why traffic engineers always require evidence counts for the specific facility they're going to design. So you may think as traffic design being almost as a custom-based design for each different type of facility. There's no standard facility, so there's like no standard template that you can apply to a facility. You need to look at them each one individually. That's why traffic engineers need to get the actual count data, actual data for that specific facility. Now we're getting into the directional factor, which is the that indicates how much of traffic on a roadway is moving in a given direction. So it is based on the percentage of the dominant peak flow direction, and typical values range between 55 and 65%. So the directional design hour volume is given as the directional design hour volume. See how I love these acronyms? This acronym is actually telling you how to find it. So the directional design hour volume is found by multiplying the direction, the predominant direction, times the design hourly volume. So if your predominant direction is 65% of the traffic, your directional factor will be 0.65 times your design hourly volume. And this can also be done by simply multiplying your direction factor times your K factor times your average annual daily traffic. And that is because we're simply solving this equation. K times the average annual daily traffic is our design hourly volume. You can see that in equation 73.2 of CERN. The directional design hourly volume is the design volume for the roadway in a given direction. Now the direction factor can range quite a bit for, let's say, 50% for a central business district where we just have the same amount of traffic in both directions. And it can vary up to 80% for rural roadways at peak hours. Think about for traffic